denk het maar tot 10 jaar. Dat is nog niet tentamen opgericht.
So I guess in a nutshell, most chapter 13. So hopefully we'll have some lectures, so we'll go into more detail. But now we'll skip towards chapter 14, and we'll talk about what happens if you don't have a convex or a concave problem, and we no longer have just a local optimum. The local optimum is over a global optimum. In that case, what we look at is the field of meta heuristics, and it's basically combining different heuristics, so applying different techniques to basically search your entire space and make sure you don't get stuck in a local optimum. Now, probably every self-respecting mathematician in the area of optimization has his own meta heuristic, so there are literally thousands of them. So we will not go into all of them, but we'll discuss some of the more basic ones. To give you an idea, one of the big problems you run into here is that your optimization method actually has to match your problem. So each problem might have a different optimization method. So everything becomes very custom in this area. So maybe the most basic and the most fixed way meta heuristic there is the so-called taboo search. Taboo search, like any other nonlinear problem, what we have to do, of course, we have to start with an initial solution. And there, what we do is we use a local search procedure to look at what is the best change we can make from our current situation. However, in that case, what we also look at is also we'll keep on looking, even if that solution is worse than the point we're currently at. So we're not only looking for downhill, so we don't stop we're at our optimum, but at each point we'll do a search around our space and define which is the best solution still from where we're at. Well, one of the issues is there, if we go to that solution and then we'll do the same search, then we'll probably end up back in where we came from. So we'll keep on jumping back and forth from one to another solution, so we'll never get anywhere. Well, how we solve that is by using a taboo. And we use a taboo list. And basically, the taboo list is only meant for one thing, and that's for blocking us from going back to the previous solution. So it actually stops us from going back to the solution we already found. Well, there's a couple of things with housekeeping basically we have to do. Well, first of all, we might not just have one, but especially if we have, for example, independent moves, we have to keep a track of and we have to block that move for a certain amount of time. And the amount of time you have to do that for is again very depending on the size of the problem, and it's a setting you need to change a lot to actually make sure you don't screw something around every time basically end up back in that solution. Of course, the last taboo move you have to block, but the one before that, well, you might actually get a combination which does give you a global optimum. So the ones before that, you do try not to use them, but you basically only allow them if they give you a new complete global best solution. So if you get a new best solution, or incumbent solution as we called it before, that in that case, although taboo move can be made, but in all other circumstances, they are blocked as well. And there's a maximum size to the list of taboo moves, so at one point you'll simply scrap them out and forget about them. So you iterate, you basically stop if you have a number of iterations, usually without improvement. So you keep on going until you have like 10 iterations without an improvement. In that case, you say, okay, this is the best solution I find, and that's what you assume is your global optimum. Well, to give you an example, a self-help example using the book, but I made it slightly smaller and slightly better to understand. In this case, we're looking at the traveling salesman problem, which basically in this case we have 5 different points which we need to visit. 1, 2, 3, 4, and 5. You see they're slightly 4 is slightly off-center, so it's slightly it's like a box which is being collapsed. And what we'll start off with is our initial solution, and our initial solution is going from 1, so we'll always start at 1. There's no point in shifting that, so we'll always start at 1. And our initial solution is going from 1 to 2 to 3 to 4 to 5, and then it goes back to 1. So in the book they have 1, 2, 3, 4, 5, 1. I left out the 1 because we always have to go back to 1. And in this case, our initial solution has a value of 51.87. So this route has a total distance of 51.87, and now we want to minimize that. So what is very important in any metric is the choice of your decision variables. So in this case, it's the order in which we visit the points. But also, if you look at a taboo search, how do we actually change these solutions? So what we use in this case is that we'll actually shift points around. So for example, well, 1 is always stuck, but we can, in this case, shift 2 and 3. We can shift 3 and 4, and we can shift 4 and 5. So we actually have 3 options here, so 3 changes we can make to this order. So if we now look, well, the shifting 3 and 2, because it's a bit small, luckily we have a big screen. So if we look at the shifting 3 and 2, in that case we shift 3 and 2. In that case you can see what we get. So 3 and 2 here is actually this black line, and what you see is that of course this is still the same. However, 2 is now connected to what 3 used to be connected to, and 3 is now connected to what 2 used to be connected to. So we've actually switched these connections for these 2 points around. So in this case we get a total distance of 54.27. If we shift 3 and 4, then we get a total distance of 51.28. So in this case we actually take these 2 lines, and what was connected to 4 is now connected to 3, and what was connected to 3 is now connected to 4. So again, we swap this around. Now in this case we get a distance of 51.28, and if we shift 5 and 4, so we have to actually take these 2 points, switch them around, we get a 49.05 as the best answer. So in this case, our best solution, which comes out, is also an overall best solution. So it's better than where we started off at. So this is our new best solution, and that's actually our next starting point. Well, in this case, 5 and 4 will actually be a taboo move, so you might see it slightly accentuated. So 5 and 4 is a taboo move. So in my next move, I'm not allowed to switch 5 and 4, but I am allowed to switch, well, not allowed to switch 1 either, but I am allowed to switch 2 and 3, and 3 and 5. Well, if I switch 2 and 3, so as a taboo list, in this case, I'll stick to the size of 1, because I don't need it. This problem is very small, and it's nice to explain how it works. But if we have, like, in the book, there are 7 points. If you have hundreds of points, then the to-do list will have to be larger, or otherwise you'll actually shift back towards an earlier move. So that's usually a bigger list. So in that case, if we switch 3 and 2, then we'll end up with a distance of 57.89. And if we shift 5 and 3, we end up with a distance of 54.90. Of course, we're not allowed to shift 5 and 4, because then we'd actually end up back here. What we see now is that, well, both these solutions are actually worse than the solution we're at now. They're actually also worse than our current solution. However, we'll still keep the best of these solutions, which is this one, and we'll actually start from there. So now we have this solution, and now it's the best solution of our iteration, but it's not overall the best. However, it's the one we'll keep. So we'll take this, and now that means that actually previous move 5-3. We'll actually taboo this, so mixing of 5 and 3 is not allowed. However, of course, we are allowed to shift 2 and 5, and 3 and 4, which we'll do. Well, if we shift 5 and 2, then we'll end up with 53.95, so that's already better. And if we shift 4 and 3, then we'll end up with 61.66. So in this case, this is actually the best solution of the iteration, which is better than our current solution. So we'll continue with that one. So we'll take this one now as a reference solution. This means now that 5 and 2, switch between 5 and 2, is actually a taboo move, but we can shift 2 and 3 and 3 and 4. Well, if we shift 3 and 2, then we end up with a length of 47.51, and we shift 4 and 3, then we end up with a length of 60. Well, shifting 3 and 2 actually means we get a new best solution, 47.51, which is actually better than our previous best solution. So this now is our overall optimum. You can also see there that if we just did a simple search and only looked around point 1, we would have actually basically ended up at the 49.05. That would have been the best local optimum. But now you see actually we're at a better global optimum. We're now at a better optimum than our local optimum. which is 47.51, and that's our overall best solution. Now, if we continue iterating a couple of more times, which I won't do here on the screen, we'll actually find a different solution with the same value, which is, I'll just switch this one on, and I'll get rid of the display box. So if we actually continue a few iterations, so now we have the best solution, which is 15324. If we actually iterate more, eventually we'll find 14235, which is exactly the same solution, but then actually in an opposite direction. And then we're sure that this is actually the overall optimum solution. So if we find a few iterations, and after a couple of iterations we'll have to stop, and we'll find that this is actually our overall optimum. We wouldn't have found it if we only did a local search. So you can also look at the book, which has an even more expanded example, but I hope this helps you understand the basic physics around the booster. Another method is simulated annealing. Simulated annealing basically mimics the cooling of, for example, a metal or glass. It's in its liquid state. When it cools down, it will start to fix at certain points. So if you heat it up and then cool it, and then you will slowly remove the strain and imperfection, so you basically heat it. Because of that, it will basically be able to become a bit more fluid and replace itself, to be able to take away the local strains and the imperfections, get everything to line up, and then but then basically go to the minimum energy state. So, well, if we cool it, then of course the energy level of the atoms tends to decrease, but you can still have some atoms which are hotter than others. So even though the overall is cooler, you can still have individual switches still going on. However, the likelihood of those will become less and less. And what we then use is a Boltzmann probability distribution to basically express the idea that if we have a thermal equilibrium, temperature T, then the energy probability will be distributed. So we'll actually have a e to the power minus e divided by k times t. That means that the lower e becomes, the lower the probability will be that we'll actually see a shift occurring. So as time progresses, the chances of a shift become less and less. Now, if we look at what does that mean, well, basically what it means is we look at the algorithms that will again take an initial solution, and from that solution we'll make a random step from the current solution. So very important word here is step. So we need to have some sort of problem in which we can make a step. So if we have an infinite number of directions we can do, but we have to make sure that here our decision variables, but also that we choose a range of steps which we can make are actually feasible from this solution. So we take a random step to a point in the neighborhood, and then if we find that step is better, then we'll simply accept it as the new solution. However, if it is worse, then in that case we'll use a probability function to actually determine the chance that it will be accepted. And that chance is then dependent on, first of all, how much worse than the old solution is it, but it's also dependent on the temperature gradient, which is a number which decreases with time. So which means that the chances it will be accepted become less and less as our iterations continue. And that a certain chance we accept it. What we then do is we pick a random number between 0 and 1. And if that random number is lower than the probability, then we'll accept it. So if we have a probability of 1, then we'll always accept it because the random number will always be less. And if it's higher, then we'll actually reject it and look at the next point we can look at. So then we'll stop after a number of iterations at the lowest, let's say, available temperature, and then we'll take the best we found overall for. So we need to have our current solution, and we of course need to remember our optimal solution, which again is same as the booster. So if we now explain that similar, now I don't have the drawings, we still have the same situation. So we still have these 5 points. In this case, again, we have our initial solution, which is 1, 2, 3, 4, 5. Now the steps we can take is switching around 2 with its successor, which is 3. The third position with its successor, which are 3 and 4, or the fourth position, which is 4 and 5. Or we can switch 1. We'll leave 1 always because we always need to start somewhere. So we'll leave 1 where it is. And of course 5, well, we can only switch backwards. So we only have 3 basic changes we can make here. So in this case, our objective is 51.87. Well, we have a temperature, a chance, a random, and an acceptance. And what we'll do here is that we'll basically, in this case, we picked at a random, we picked 3. So we pick a random number 2, 3, or 4. In this case, we pick 3, which means we'll swap around 3 and 4. So we now have 1, 2, 4, 3, 5. So it's 51.28. In this case, our temperature now is 10. Well, it's a better solution, so we'll always accept it. Well, that means we don't have to pick a random number, so we didn't leave it at 0. And of course, in this case, it's the best solution, so we'll accept it. Now, what we do is, again, we pick a random number. So in this case, we pick 4. So 4 is actually the one we're going to change with a successor. So 1, 2, 4, 5, 3. Now, as it says, it's actually a worse solution than what we already had. It means that actually the difference is about 4. The temperature is 5. So we have 4 divided by 5. So e to the power of minus 4 divided by 5 is 0.45. So we have a 45% chance it will be accepted. We pick a random number, which is 0.32. So actually the random number is lower than the 0.45. So in this case, actually we'll decide to accept it. So it's a worse solution, but we'll still accept it. Now the temperature in this case, we've halved it again to 2.5. So now we've actually picked as a random number from 2, 3, or 4, we've actually picked 2. So now we're going to swap 2 and 3. So we've actually swapped around 4 and 2. So now we order 1, 4, 2, 5, 3. The objective is 57.30. That's worse than the objective we had. The temperature is in this case 2.5. That means that the probability, so the difference here is about 2 divided by 2.5, so it's about 0.8. Minus 0.8, so 0.4, 44% chance we'll accept it. However, the random number we draw is higher, so we'll actually reject the solution and we'll look to a different option. So now again, we pick a random number, the temperature stays the same. So now we actually switch, so we're taking this solution, but now we're switching around the 4th position, which is 3. So we're switching around 5 and 3. So now, well, we get a new solution, which is 51.28. The temperature is still 2.5, so we're still in the same iteration. Now it's a better solution, so we'll accept it always. It's a better solution and we'll accept it. However, it's not overall best, but it's it's actually the same. So it's actually the same solution, but it's better than the one we had, so we'll accept it. So we've actually jumped back here. Now we'll do that again. So now we actually pick the number 2. So now we end up with 1, 4, 2, 3, 5. In this case, actually we'll end up, we found the best solution, 47.51. It's the best solution actually, so it's a better solution, but it's also the best solution. So we'll always accept it. So the chance of exception is 1. Now we'll keep on looking. So in this case, we've chosen to change the 3rd position. So now it's 1, 4, 3, 2, 5. 53.95, so it's actually about 6.5 higher. The temperature now is actually quite low. It also means that actually the chances of this are very, very low. It's less than 0.005. So it's very low. And if we then pick a random number, the chances of that random number will be higher and very high. So we won't do it. So worse, so we'll reject it. Again, same temperature. We'll try again. Well, now we've actually tried all the solutions around this solution. So in this case, actually, well, again, we're now doing 3 again. And basically, in this case, we've done a number of solutions. We haven't found a winner. This is actually the best one we found. So in this case, we're using actually 2 random numbers. First of all, we're randomly picking a change, and we're randomly picking a number to determine if that change is worse, if we'll accept it or not. So we're picking 2 random numbers.
Why do you pick a random number between 0 and 1 instead of maybe just 0.5 already?
Because you want to, because then you always end up with the same solution. So you want to have it, even though a solution is worse, you don't want to dismiss it. Even if solution is infinitely worse, there's almost an infinitely small probability it will be accepted. So you don't want to throw any solution away, but you do want to, so you want to give it some chance, but not too much. So I'll have to give you a bit of an idea. That's the idea. Yeah. Of course, as time progresses, the chance of a worse solution being accepted will become smaller and smaller. So So at one point, there's, in this case, with a temperature 0.065, it means that the objective, if it's more than 0.625 higher, the chances it will be accepted are very, very low. So they're less than, what is it, minus 0.4. To continue, so the temperature, of course, decreases. So in this case, we have it every time, but you can choose different temperature steps depending on your situation. So what you see with most meta heuristics is that there's a lot of settings you need to change, and your settings can have a massive impact on how your optimization functions. So a local optimum you'll find, or whether you find a global optimum, is very dependent on a whole bunch of settings. So in this case, the temperature cooling scheme you're choosing, if it's linear or if it's, in this case, a negative exponential, that really completely changes the behavior. In this case, of course, I chose something which fitted my need. But if you're looking at a very big problem, you're often a lot of time you're actually changing your settings to find out how different settings work. So there's a lot of trial and error involved in these methods. And even then, you're never guaranteed you'll find the exact optimum. So it's always going to be a guess. So if we then leave a look at a bigger problem, and also so today I have a couple of optional homeworks that actually last year they were really part of the problem. They're more like run this and see what happens type of exercises. So that's why I've left it as optional, but I do suggest you run it. So we have a couple of MATLAB programs basically showing in this case also simulated annealing, what a simulated annealing optimization model looks like. And there you can basically see that it basically springs all throughout, and basically at one point it centers, and hopefully in this case it will center right in the global optimum, but there's no guarantee. It might actually, because of the randomness, jump to a local optimum and actually stick there. So if you run it a couple of times, then what you'll see is that probably every time you'll end up with a different solution, or at least the way to the solution will be different every time. Then genetic algorithms. Who of you have heard about genetic algorithms? Most of you. Some of the rest of you probably heard, but you don't dare to admit it. Genetic algorithms, well, they basically mimic the process of natural evolution, which we often also joke about, well, it basically means, the thing it mimics mostly is that it takes billions of years. They're not very efficient. But what they do is it's an interesting way. They're actually perfections. So we'll talk about evolutionary optimization, which is already an improvement. But basically what it does is that if we look at the process of natural evolution, and we look at genetics, then basically what we have is with people reproducing themselves and survival of the fittest, we basically apply that to our optimization method. So what we need for that, of course, first of all, is a population of solutions. And again, there you have a variable of your population size. If you take a big population, your problem becomes a lot bigger, but there's much more likelihood of you finding an optimum. But if you take a smaller population, you probably can do a lot more iterations. So again, there is another setting you have to tweak when you're using a meta heuristic like this. So if you have a promising solution, you're giving them a larger probability to reproduce the appear in the following generation. So again, here there's a probability. So again, they're using random numbers. And also what we use there is a crossover. So we're looking at ways in which we can combine different solutions into a new solution. So also here there's a trick and what are my decision variables and how can I combine them to a new feasible solution. So what you really want to do is minimize the amount of infeasible solution you get. I think you refer to them as stillborns in this case. So if you combine it, you actually might have, for example, in traveling salesman end up where you have 2 times visiting 5, which is an infeasible solution, and you can throw that away. So what you want to make sure is that you pick it and cross it over in a way in which you actually get feasible solutions. Next to that, they also use another method, which of course is also part of genetics, and that's mutation. And what we do there is that we randomly change, in case we have binaries, we randomly, and usually we use like 10% probability, randomly change one of the variables to actually get a completely new solution which is unrelated to our parent. And this allows us actually to get something new instead of converging to a certain point. I'll just show you the way of crossover, and this is also how the book models. So in this case, we have 2 solutions, which are the parents. Right, so we have 1, 2, 3, 1, 2, 4, 5, 3, and we have 1, 2, 3, 4, 5. So we have these two now are chosen to be our parents. So now how do we combine these? So well, of course, like in previous problems, the one is set, so we could change it, but then we're just starting at a different point. We don't get a unique solution. So in this case, this one shouldn't be here yet. That was supposed to be the surprise at the end. But in this case, we'll start with one. So one is always the starting point. Now we'll look at both of the parents to what the one is connected to. So in parent one, the one is connected to 2 and it's connected to 3. And for parent 2, it's connected to 2 and it's connected to 5. Yeah. So that means we can either now pick 2, 3, or 5. So those are the option 4 is not an option 4 is not connected. So now I'll ignore mutation in this case. If you have a mutation, you can have a random chance, a 10% chance it will mutate. And then there's well, in that case, there's only 4 available for mutation, so it will take that. But in this case, it's either 2, 3, or 5. So in this case, I think I picked, so 2, 3, or 5 are the options. So randomly we pick one of these, and in this case it's 5. Now we look at 5. Where is 5 connected to? Well, 5 connected for parent 1 is connected to 3 and 4, and for parent 2 it's connected to 4 and 1. But we've already had one, so we'll eliminate that. So the only option we have is 3 and 4. So 3 and 4 are actually what was supposed to be from 5. Okay. So this should be from 5, so it should actually be from here. So 3 and 4 are the options. We'll pick one randomly. In this case, we'll pick 4. Now we look at where's 4 connected to. Well, 4 is connected to 2 and 5. However, 2 is already used, so we can scrap that one. 4 is in this case connected to 3 and 5. So we actually have in this case 3. So 4 is connected to 2, and 4 is connected to 3. So we have the option of 3 and 2, which are still available. So again, randomly you pick one. In this case, we pick 2. And of course, then we look at where is 2 connected to. Well, 2 is connected to 4, and it's connected to 1, and 2 is connected to 1 and 3. However, 3, of course, is the only one available. So it has to be 3. So now we're basically combining the 2 parents. We've created our child solution. And it basically has a solution of 54.27. Now, we usually do this a couple of times per parent. So let's say normally like 5, what is it, average 2.3 used to be, now it's like 4.8. No, but we do it a couple number of times per parent. So we randomly select our parents with a probability distribution where the best parents get a higher chance of reproducing than the worst parents. Then we generate a number of children, so usually like 1 per parent, so 1 per couple. And then what we do is that we basically take a certain number of children, a certain number of parents, and then we combine them into a new group. And basically we cross them again. Which can also mean the parents are actually crossing with the children. So for genetic optimization, that's okay, but everywhere else it's not. So that's hopefully a difference with real life. So, well, mutation not shown here. So in that case, what we'll do in this case that there's a random chance we get a non-connected link and selection. So usually what we actually do is we keep all the children. So only 50% of the parents reproduce. So we get 50% of the original population as children. We dump half of the parents, replace them with the children, and that's our new set for the next iteration. Also something, in some cases, and that's also in the book, is that you actually have, for example, you get 4, which is actually not connected to anything new. And in that case, you can also use a switch over like we used before. But that's described in the book. But this shows the basic premises. So, how does it work? Well, first of all, what you'll see is actually, if you look at more complex problems, and this is a simple problem, but usually what we do is that we initialize the population of chromosomes. So in this case, chromosomes are the order in which we visit the nodes. We evaluate the fitness of each chromosome, so each of our parents, and we basically select them based on the fitness, and usually we'll use a random distribution so that the better they are, the higher probability that you're selected. And then we encode the chromosomes to binary strings. And this is really where there's a trick, so we should do this in a way that if we change it, it's still feasible. So again, we want to minimize the amount of children that, the infeasible children that are created. So this is really where we have to do that. So we create a children chromosome by mating parents and applying them. So in this case, we'll do it slightly different than I just showed. In that case, we'll just, like with real chromosomes, we'll cut it and fix them together, and we'll form a new population of children, part of the original population, part of the children population. So yeah, we'll get inbred there. And then we'll decode the population again. So we'll do that for a number of times. And we'll, for example, in this case, we'll stop with the maximum number of generations. So we'll continue to like 1,000, 10,000 generations with the typical numbers, and then we'll stop. Well, again, there's a whole bunch of things. So an important one is the population size. So how many do we take into each iteration? Again, a larger population size will mean that you'll have more solutions to work with. However, each iteration will take longer. So the trade-off here really is computational time. The crossover probability, so what is the probability that the parents will work together and be crossed over? What's the probability of a mutation? So normally this is like 10%. So what's the chance that a gene will randomly change? Well, the reproducing fraction and so how much the parents will actually reproduce. So with 50%, then we'll end up with 50% a new population, and of course the number of generations. So all of these you have to try it out and run it multiple times to see how this works on your problem and when it actually works or not. Well, in alternative information, in this case we use permanently encoded forms. So in this case we use binaries. That makes change very easy because something can change from 0 to a mutation is having something go from 0 to 1 or something from 1 to 0. So it makes our steps very well binary, I almost say. So we have very clear steps we can take, but then how to actually put that into this form is where the trick is, because again, all the options have to stay feasible. So the choice of your decision variables and then the choice of how you combine these chromosomes is very important. So and then basically what we'll do is basically when we cross over this is that we well, of course we look at the problem as a solution. In this case, it's different. So we basically what we do is we take two genes, we take a random point within these genes, we'll cut it in half, and then we combine the two genes of the parents in this case. In this case, a typical value for crossover rate is about 0.6, so 50–60%. So in this case, we'll cut the genes and put them together, much like happens with real DNA. So mutation, in this case, is still so mutation is really about making sure that we explore the full search space and we don't get stuck in like this fixed group of parents and children, and we keep on keeping in the same direction. I don't want to make a joke about certain villages in the Netherlands, but I won't. So you want to make sure that new things happen, so you do go outside your comfortable space. And in this case, mutation is applied after crossover. So first we'll cross it over, and then we randomly pick mutations within the DNA. So mutation again will change a single bit of the chromosome. A typical value for the mutation is 0.1. So genetic, it's quite a powerful method. It's very broad. It has a lot of potential. The big problem with genetic is that it requires a lot of computational space time. So it's relatively inefficient. So it takes and because of that, what we'll actually see is that most people will actually prefer to look at a different evolution algorithm, which is very similar. However, especially so we selected so you can actually have a higher percentage converge. The convergence is better with the differential evolution algorithm. It's not discussed in the book, by the way, but especially what's changed is the procedure of creating children. You do that in a much better way, so you actually converge to an optimum solution much better. So you can actually get a more simple performance at a significantly lower number of calculations and evolution. So that's why we call it differential. So if you do have to use this, and differential evolution is usually a better way than a standard generic algorithm. So again, time for you to ask some questions. So which methods will always produce the same result without a fixed random seed? So I discussed a couple of measuristics, but which one of these will actually, if you run it 10 times, you'll always get the same answer? Start the timer. 30 seconds, so I'll stop it again after 10. So 4, 3, 2, 1. Let's see. Good. 70% of you got it right. I'm not sure exactly just read it for the last 3. But at least it's taboo search. So one of the nice things about taboo search is that it's opposite the other. It doesn't use any random numbers. So it will always, if you give an initial solution, it will always end up with the same path. It will always take the same path for the final solution. So it's nice and reproducible. The other one's actually, what you can do, and that's why I mentioned it, you can do the fixed random seed. So if you talk to computer programmers, first thing say there's no such thing in computer programming as a random number. They're not random at all, but they're numbers picked in a certain sequence, and often you have things in there like the time in milliseconds generating the random numbers. And one of the things you can do is that by using a random seed, you can always get the same sequence of random numbers. And in that case, of course, even with the simulated annealing and genetic algorithm, you can actually get the exact same result. However, if you use a fully random, which again is arguably not possible, you always get a different solution. And taboo, again, you always take the same steps. There's a clearly predefined path you take, so it doesn't use random numbers. Finally, the download simplex, which is not discussed in the book. But again, if you have to solve a problem, then it is something interesting to look at. It's also known as Melder-Mead method. And basically what we use there is a geometric way to go through our search space. Well, it can be applied for non-linear concave or convex as optimization problems. And the main advantage of this method is that you only have to use function evaluation and you don't have to look at derivative. So again, like I said, if it's a nice algebraic function, you can determine the derivative. It's not a big problem. But again, if it's a black box or if it's a very complex combination of lookups and things like that, then it's and especially, for example, if you have binary problems and you don't even have derivative, then this is still a usable method. So, well, this method is not very efficient in terms of number of evaluations, but it does basically work. So that makes it more of an engineering approach, I would say, than a mathematics approach. So how it basically works is that, well, we have a geometrical scheme, we have a couple of unknowns, and then it works with the number of +1 in its parameter combinations, and basically what you end up with is a geometrical figure, which is a triangle for if we have a two-dimensional search space. So if we have 2 variables, and if we have 3, it's a tetrahedron. And basically what it does is it applies a series of transformations applied to the simplex. It has nothing to do with the simplex method, by the way. I'm not exactly sure why it's called simplex, but it has nothing to do with the simplex method called in previous chapters. But it basically uses a simplex as a shape, and it uses a series of transformations to basically get towards an optimum solution. So it basically explores the parameter space, sort of explores the solution space within and around it to expand and contract and move around, basically contract an optimum if you allow it in long enough. So for that, it uses a couple of possible steps. So if you have a high and a low probability, it can basically expand. It can reflect, so it can actually go towards the opposite. It can lengthen, it can contract, and that way it will basically, as a shape around your optimum, it will basically at one point converge. So it's something to look into if you're doing an optimization. So, well, one final question. So if we have a number of methods, which of these methods would actually allow you to have multiple solutions? So what now if you want to have not just one solution, but where you want to create, for example, a burrito front, and we want to have a whole range of this solution. What method do you best use in that case? I'll start the timer. I'm guessing you're hungry and want to go to lunch. I think I only have one slide after this, so I won't skip back. Okay. Yeah, indeed. So one of the powers, of course, the genetic algorithm has is because we have this population, is that we always still at the end have this population. So especially that allows us to actually take the entire population and look, okay, what's the variance in there? So if we're looking at having like a whole range of solutions, then genetic algorithm will do that. But actually all of the other methods will only basically optimize to a single point, and that's a single solution we'll get. So that's one of the powers of genetic. If we, for example, have a multi-objective, then it's a much better way. So final remarks. IOR also has a tutorial error for meta heuristics. It's not part of the homework, but it's very interesting to look at. So it has a taboo search to simulate needling in genetic algorithm. So it's more like a demo in that case. So it has certain fixed parameters and it shows you how it goes through the iteration. So maybe above this will give you a bit of a feeling of what does the method actually do. So definitely suggest you have a look at it. It's difficult to ask really questions about it in the homework, so that's why I'm not doing that. Again, also because the solution is every time different. So have a look at that. Also, there's optional extra assignments. They use MATLAB. It's already done by the person who did it before me, and Snella created a couple of MATLAB scripts which use simulated needling and genetic algorithms, and they can see basically what a run does. You can change parameters, and it will show you a bit how that works. So simulated needling and genetics is also on there. Okay, that's it for today. I'll post some more announcements on